Hello everybody and welcome to this second video about rates of reaction for GCSE chemistry. In this video we'll be looking at what a typical rates of reaction graph looks like. Then we'll move on to consider what the two different types of graph look like for rates of reaction. We'll then look at how we can work out rates of reaction from a graph, and this will take two parts. We'll be looking at the mean rate of a chemical reaction, and we'll also be looking at the rate of reaction at a certain time during that chemical reaction. And then last of all, we'll be looking at comparing the different types of graph for chemical reactions, and this is something called relative rates. That has been made. Before we go straight into looking at graphs, we need to first have a look at how we would collect the data for a graph. First of all, I should say that this depends on what type of experiment it is that you're doing, whether you are collecting a gas on here. So this obviously would be the gas that gets produced, and you'd be looking at measuring the volume of the gas that gets produced as time passes. Alternatively, you might be looking at this experiment that we looked at in the previous video, where you've got some acid maybe here that is bubbling, and we're making a gas, but that gas is then escaping out of the container through a piece of cotton wool. And what we'll be looking at here is we'd be looking at the mass drop recorded on this balance. So this is the piece of equipment called a balance. But what both of these techniques have in common is that they both use the same equation for working out rate of reaction. So the rate of a reaction is the quantity of product divided by the time it took to make that product. Alternatively, we could consider it to be the quantity of reactant that got used up divided by the time it took to use up that reactant. But essentially we're doing the same thing. We're taking the quantity of substance used or made and dividing it by time. So obviously what we would need to use is we would need to use a timer or a stopwatch. Both of those names for the equipment are acceptable, but not really any alternative. In terms of the data that you'd collect, you'd obviously have to have a results table, and I've got the beginnings of a results table here. You'd need to collect two pieces of data. First of all, you would need to have the time, normally measured in seconds, and then you would either have the volume of gas in cubic centimetres. That's obviously the gas that is being produced in this experiment up here, or you would have the mass of your chemicals if you'd been doing this experiment over on the side. But let's us start by having a look at the volume of gas produced experiment. And so what I'll do is I'll just quickly fill in some numbers. We would maybe measure the volume of gas that had been produced at regular intervals, perhaps every 20 seconds. And so that's 100 seconds of collecting data. So at the beginning, at time 0, we haven't made any gas because the chemical reaction hasn't started. So we would have 0 on there. And then maybe the gas would go up to 30 cubic centimetres of gas produced in that first 20 seconds. And then after 40 seconds, the volume would have increased further. Now it's gone up to 50. And then it goes up to 60. Remember, this is a total volume that has been made so far. And then it goes up to 65. And then it goes up to 65. So it stayed at 65 on there for this set of data. If you'd been measuring the mass drop, you'd get something really, really similar, except of course you would be measuring not volume, but the mass of the chemicals. So you'd still have time and you'd have mass of your chemicals in grams, and then you'd expect the same sort of pattern. Measure the mass every 20 seconds or so, and you would expect this mass to go down in a similar sort of pattern to in the previous experiment. But obviously the numbers are going down this time instead of going up. We've just looked at how you might collect the data. Now, you could be required to draw one of these graphs from data that you get given in the exam, but for now let's just look at what shapes these graphs might typically have. So the graphs will always look in the same sort of format, so you'll have time on the x-axis down here, usually in seconds, but it doesn't have to be, and then you'll have the amount of product formed, which would typically be volume of gas, but not necessarily. Now, the shape of the graph would characteristically look like this. It always starts at 0, 0, even if 0, 0 isn't marked on the graph. I'm not going to use any numbers for this first graph, but it would typically look something like that. And this is a really characteristic shape for a rate of reaction graph, and it's got three key sections. The first section to note is that the reaction is fastest at the beginning. We'll explore why in a moment. Then next to note is that the reaction slows down, and then last of all, at some point, the reaction ends. And we can see that the reaction is ending because no more product is being made, so the reaction is over. Now, what's really important to note about this graph is that the gradient is directly related to how fast the reaction is happening. So in terms of the gradient, if you have got a steeper line, steeper gradient, it will be a faster reaction, which again is further evidence to show that this is the fastest part of the reaction, because we've got a very steep line here. It slows down, so it's nowhere near as steep as we get further on, and then it ends here. It's flat line, it's plateaued is another way of talking about it. This reaction is over. Alternatively, if we just move this graph over to here in this corner and we sketch a different graph, if we were to sketch a graph for how the mass of chemicals changes over time, it would look something more like this. And at first glance, this looks really quite a different graph because it's the opposite direction of travel. However, we've got the same characteristic sections. So the mass of reactant goes down very quickly at the beginning, and so this part of the graph is for the fastest part of the reaction. And then the reaction gets slower once again, and then the reaction stops because the mass of the reactant is not going down anymore. It's reached its minimum point. Let's explore now why the rate of a chemical reaction changes over time. So here we've got two reactants. We've got the blue particles and we've got some green particles, and they're all moving around together in a reaction mixture. Now, at the beginning of the reaction, when the particles collide together, they are going to react. And once they react, these reactant particles are used up. So let's collide a blue particle and a green particle together. So at the beginning of the chemical reaction, the concentrations of the reactant particles is at its highest, and so the frequency of successful collisions is also at its highest, and so the rate of reaction is at its highest rate. Now, as time goes on in the reaction, reactant particles get used up because more and more of the green particles collide with the blue particles, and so the concentration of the reactants goes down. And that means that the collisions become less frequent, and then the rate of reaction is going to decrease. Now, if we continue this reaction on until all of one of the reactants has been used up, the rate of reaction is going to drop to 0 because one of the reactants, its concentration has dropped to 0. So there are no longer any green particles for these blue particles to collide with, so the rate of reaction is 0 because there are going to be no successful collisions. Now, obviously what we could have is we could have all of both reactants being used up, but that's actually rarely the case. Normally you've got one chemical left over because it was in excess at the beginning, and one chemical gets totally used up. So to return to this characteristic shape of the graph, we've got these three distinct regions. We've got the fastest part at the beginning, then it slows down, and then the reaction is over once it flattens out, so the reaction is over. And the reaction's fastest at the beginning because, as I say, the reactants have got their highest concentration that they're ever going to have. And so therefore, we're going to have the most frequent successful collisions at any point in all of the reaction. That's right at the beginning. And the reaction slows down because the reactant concentrations decrease as time goes by, and that therefore means there will be less frequent collisions and less frequent successful collisions. And the reaction is over at the end because one chemical is used up, and therefore there are no successful collisions. There might still be collisions because there's some particles there, but none of them are going to lead to a chemical reaction. Let's have a look now at how we can work out the rates of reaction by using graphs. First thing to note is that this is one of the graphs where we make a gas. So we've got the volume of gas that has been produced on the left-hand side, and we've got time on the x-axis, volumes on the y-axis. Now, as you can see, we've got some numbers on the graphs this time. And let's imagine we've been asked to work out what the mean rate of reaction is for the whole reaction. Now on this occasion, the first thing that we need to do is we need to look for the point when the reaction is over. And the reaction is over once no more gas has been produced. And that is somewhere, I think, about here on the graph. And the graph has gone flat. And that means that no more gas is being produced. And what we have to do in this case is we have to look down, first of all, to the x-axis. And we find out that the reaction is over after 60 seconds. Then we have to look across on the y-axis to how much gas was made in that time. And as you can see on here, we made 120 centimetres cubed of gas in that 60 seconds. And so the mean rate of reaction for the whole reaction is the volume of gas divided by the time it took to make that volume. So for this graph, we made 120 cubic centimetres in 60 seconds, and so the rate of reaction is 2 cubic centimetres per second. Now let me be clear, this is the mean rate of reaction because obviously, as we know, it's faster at the beginning and then it slows down and then it's really, really slow just before it ends. Let's have a look at how we'd work out the mean rate of reaction for the whole of this reaction, where we're not collecting gas, but we're looking at the drop in mass of a particular set of chemicals. So once again, we need to look for the end of the reaction, and once again, the end of the reaction is 60 seconds because it is flat after this point. So the reaction is over, it's finished. Now this reaction is a little bit harder on here because we're not going back to 0, 0 in both of these cases. For time we are, so 60 seconds of time has passed, but the mass began at 50 grams and it has gone down to, provided my graph looks reasonable, it's gone down to 40 grams. It's not perfect, but we're going to assume that it is. So it's gone down from 50 down to 40. So that is a decrease of 10 grams on here. So the mean rate of reaction is the change in mass this time, so that is 10 grams decrease in mass, and it took 60 seconds for that change to happen. So 10 divided by 60 is the calculation we need to do, and that works out at 0.167 grams per second to 3 significant figures. Let's look now at how you can calculate the mean rate of reaction between 2 points in time of that chemical reaction. So let's imagine they've asked us what the rate of reaction was between 10 seconds and 30 seconds. And so what we have to do is similar to what we've done in the previous graphs, but it's a little bit fiddly because what we have to see is we have to see what is the volume of gas produced after 10 seconds. Use a ruler obviously for these. I haven't got a ruler to use with this app, but you'd use a ruler on your exam paper and you'd read along to the y-axis and you'd find out that 40 cubic centimetres of gas was made after 10 seconds. And then you'd do the same thing for 30 seconds, so you'd read up to the line and you'd find out that 90 cubic centimetres had been made after 30 seconds. And so the rate is the volume of gas divided by the time, and the volume of gas that had been made in that 20-second period in time is 90 take away 40. And the amount of time that took is 20 seconds because it's 30 take away 10. And so the sum that you're going to put into your calculator is 50 divided by 20, which is 5/2, which is 2.5 cubic centimetres per second. You can do the exact same thing if the mass drop is what is being measured in this reaction instead of gas volume. So let's do the same sort of thing, but let's have slightly different timing, and let's say what is the rate of reaction between 10 seconds and 20 seconds on here. So the same thing needs to happen. We need to find out what the mass was at 10 seconds. And so you need to get yourself a ruler again and read up to the line. And I'm going to call that 46 grams is the mass at 10 seconds. And then at 20 seconds, we're going to call that 42 grams. So that means the mass has dropped by 4. But the rate is the mass drop in that time, not for the whole reaction, but in that particular time period, divided by how long that time period was. So it's 46 take away 42, divided by 20 take away 10. And so that works out to be 4 gram as a drop in 10 seconds. And so overall, that is 0.4 grams per second. So that's the rate, 0.4 grams per second. Now we're going to take a look at how you work out the rate of reaction at a specific point in time in that reaction. And so the first thing that you have to do is draw a tangent at that particular point. And a tangent is a straight line that just touches a curve at that particular point and sort of follows the line that curve had at that particular point. So what I mean by that is if we looked at 0, 0, and we looked at the tangent at the beginning, so the tangent would be a straight line that sort of follows the curve at the beginning. And then let's draw another tangent later on in the reaction. And so this tangent is for the rate of reaction not at the start, but at this point on here. So that tangent is for 25 seconds during the reaction. And then let's add another tangent at the end of the reaction, and you can see we've got a line like that. And so remember what we've said previously, that the gradient is proportional to the rate. And so a steeper gradient means a faster rate. So first of all, quick word about tangents. When you're drawing a tangent, you must always use a ruler and a sharp pencil to make sure your tangent is nice and clear. The reason that you want to draw in pencil is the same as why you should always draw graphs in pencil, which is because if you make a mistake, you can rub that mistake out. Let's explore now a more focused example about drawing tangents. And so let's imagine this is our graph and we've been asked what the rate of reaction is at 20 seconds. Now let's be really specific. First of all, we need to find 20 seconds on our graph. So 20 seconds is down here, and we need to read up to our curve. And now we need to draw a tangent at that point on the curve. And I've done that here. The distinctive thing about tangents is, first of all, they need to meet the curve at the point in question, 20 seconds, and there needs to be an equal amount of space between the curve and your tangent on both sides of the line. So you can see here the space that I've got between my curve and my tangent, and the space I've got here between my curve and my tangent. It needs to be equal both sides. Now, this first tangent that I've done is probably just about big enough, but it's a really good idea to draw your tangent nice and big so it's really easy to use when you're calculating the gradient of that tangent. So what I'm going to do is I'm actually going to get rid of that tangent and put in another one instead. Now, I like this one better for two reasons. First of all, it's bigger, and so it's a lot easier to read. And the second reason I like it is more significant, and that is that it meets the y-axis, and that makes it really easy to use. Let me explain how you use a tangent. So the tangent, importantly, is a straight line, and so for a straight line, you can work out its gradient by working out what the change in y is, and dividing it by the change in x. And so that means you need to find out where your tangent is with respect to both axes at the beginning and at the end. And so the reason that I've continued mine to the y-axis is that I know that this ends at 30. So the lower portion of the y-axis is 30, and then the upper portion of the y-axis is 110. It's really good to have obvious points for your tangent. So I've got 110, take away 30, which is 80. That is my change in y. In terms of my change in x, the other good thing about it meeting the y-axis is that x is 0 at its lowest point. So I'm taking away 0 on here. And at its highest point, it's come to about here, which is not an easy point, but I'm going to assume that's 45. Obviously, read your graph paper carefully on here. So it's 80 divided by 45. Which, when you plug that into your calculator, you get 1.78 centimetres cubed per second. If the reaction is one where the mass is going down, you do the same thing. You still need to work out what the rate of reaction is at a particular point. And so from my point on here, where I've drawn my tangent, I'm actually working out the rate of reaction after 15 seconds. And so I've drawn my tangent already. And my tangent meets both axes this time, which makes our life even easier. So at this point here, it's met at 47.2. Let's say it's not met at a nice easy point, but at least it's met a point that's easy to read. And down here, it's at 38. And so the change in y for our gradient is 47.2, take away 38. And then we need to divide that by the change in y, which I'm going to say that is 35, and the lowest point in x, I should say, not y. So the lowest point in x is 0, so it's 35, take away 0. And so what that means is I'm going to be doing 9.2 divided by 35 for my rate of reaction, which when we plug that into a calculator gives us 0.263 grams per second to 3 significant figures. I should point out that the rate of reaction is the same value as the gradient, but it's not the same sign. That's particularly relevant here because the gradient actually here is going to be a negative value, but actually we're only interested in the steepness of the line, and a steeper slope, remember, is a faster reaction. And so actually, strictly speaking, the gradient here is minus 0.263 grams per second, but when you're using it to calculate the rate of reaction, we're not interested in that negative sign. We're just considering it to be a value. We're going to finish off this video by just looking at a few instances where we're going to be comparing relative rates of reaction. And so before we have a look at that, let's just remind ourselves about the crucial aspect of this, which is that the gradient of a rate of reaction graph is how fast the reaction is happening, and that the final height of the graph is related to how much product you're making, which is also related to how much reactant we are using. And if you're using more reactant, obviously you're going to make more product. So I've got a line here that I've already drawn, and let's say we do the same reaction, but it's faster. And so here is a faster line. But everything else about the reaction is the same, and so the reaction is just steeper because it is faster. And then maybe we do the reaction again, and it is slower, but it's still making the same amount of stuff. And so it levels off at the same point. And you need to be able to add extra lines to graphs that you've already been given in an exam. So let's imagine that's what the question was. We've been presented with this graph and we've been asked to add a line to indicate what the reaction would look like if we used a catalyst, but everything else was kept the same. So you need to consider what is different each time and what is going to be the same. And so if we use a catalyst, catalysts speed up reactions, but everything else is unchanged. And so the reaction here would therefore be, when we use a catalyst, it is going to be faster. And so our gradient needs to be steeper, but it needs to level off at the same point. And let me be clear, in an exam, we will only be interested in the two parts on here. We'll be interested in the beginning, that will be the first point, how steep is it, and then the end on there, where does it flatten out? And let's just make sure we're being a little bit neat about this. And in fact, in an exam, let's not have any feathering to any exam lines that we do. Let's have this line nice and solid and confident and following on there. Now we've been asked a different question. We've been asked to add a new line to this graph for what would happen if we changed the temperature. Now, as we know from the previous video, temperature affects rate of reaction. If we increase the temperature, we will increase the rate, and if we decrease the temperature, we will decrease the rate. So that's a nice, easy relationship on here. So if we make the reaction colder, we'll have a slower reaction, and so the gradient will be more gentle, but it will reach the same point. If we make the reaction much hotter, it will be much steeper reaction, but it's still going to level off at the same point because we're making the same amount of chemical, because all we've done is change the temperature. This situation is a bit different. If we're changing the concentration, what will our curve look like? Let's be more specific. Let's not change the concentration. Let's halve the concentration. And so if we halve the concentration, two things are going to happen. First of all, the reaction is going to be slower because there's going to be fewer particles of reactant in the same volume. And not only that, because there's fewer particles of reactant, we're actually going to make less product. Because the amount of product that you make depends precisely on the amount of reactant that we use. So here's our 2 points. First of all, it's going to be slower. So that's point number 1. And secondly, we're going to make less product. So that's going to be point number 2. Now, we can be even more specific than say make less product. So I'm going to get rid of that. We're not going to make less product. We're going to make half the amount of product that we made in the previous line. And that's because we've used half the concentration of chemical, which means we're going to make half the amount of product. And so this curve is going to reach half the original line. So what I would do in an exam is I would get that distance, I would measure it, find the half point, which I think is about here, and that's where I want my line to hit, and that's where I want my line to flatten out. And this would obviously work in the other direction as well. If you had a larger concentration, you would end up with a faster reaction, but also you would make more product. And the amount of product that you make is directly proportional to the concentration of the reactants that you use. Or the volume, in fact. They might be sneaky and they might say we have a greater volume of something that has got the same concentration. And so what that would look like is what I'd like to show you now. And so if we've got a greater volume but the same concentration, then this time the only thing that would be affected would be the final height of the chemicals. Because we've got a greater volume of a particular solution, maybe the acid, we will make more product. But because it's the same concentration, the gradient ought to be the same for as long as you possibly can. Now obviously because we're going higher, it can't be an exactly identical gradient all the way through. To continue it along for as long as possible. And like I did on a previous graph, I've just tidied up the end point just to make sure there's no feathering to the line. So we've made more product because we've used a greater volume of solution. And the final situation to look at is about surface area, because we know that surface area affects rate. So if we have a greater surface area for the same volume of a particular solid, what we would have is we'd have a faster rate of reaction. So the rate of reaction would be faster, but we'd end up at the same point on here. So we've made what we're going to make faster, but we've made the same amount. And if it was a smaller surface area, the rate of reaction would be slower and the gradient would be more gentle. Okay, that's the end of this video. I hope it's been useful. I'll release another one about the required practical for the rates of reaction topic, but otherwise that ends the topic. Thanks very much for listening. I hope it's been useful, and I'll see you again soon. Bye bye.